In this video, we'll use calculus to study the motion of a particle in one dimension. In one dimension means that the particle is on the line, it can go back and forth on the line, but it has to stay on the line. So the position of the particle on the line is given by one coordinate, which we call x of t, and that's a number. That gives the position of the particle. Sometimes you'll hear people use displacement instead of position, but really what we're looking at here is more position, because displacement is when there's a change in position. If you go from one point to another one, there's a displacement from the first point to the second point. And here we're not looking at that, we just want to know where the particle is. So x of t is our position. The particle's velocity measures how position is changing. And when you want to measure change, you can do this with a derivative. So the velocity is the derivative of position. This is the same expressed in a different language. Acceleration measures how velocity is changing. So it's the derivative of velocity with respect to time. Same thing with a different notation. And since the velocity itself is the derivative of position, acceleration is the second derivative of position. The speed is slightly different because x, v, and a, so position, velocity, and acceleration, are numbers which could be positive or negative. The speed is the absolute value of velocity. As such, it can never be negative. Let me clarify this on an example. If I tell you that a particle has a velocity of minus 3 meters per second, it means that the speed is 3 meters per second, and the fact that v is negative means that x is decreasing. So if x is decreasing, that's because your particle is moving to the left. So the sign tells you in which direction the particle is moving, and this, the absolute value, tells you what the speed is. One last word about vocabulary. We say that a particle is at rest or stationary when the velocity is 0. By the way, this is where the word stationary point comes from. These were the points where the derivative was equal to 0, and here the derivative of position is equal to 0. Let's try this on an example. If you feel comfortable, well, you can just pause the video and try for yourself. So we want to find for what time or times the particle is at x equal to 0. This is a nice one because they're giving us the equation that we need to solve. Position is x and x is given. So we just write this down and that's equal to 0. We don't have a formula to solve cubics, but we know that whenever we want to solve something equal to 0, what always works is to factorize. When it's degree 2, what the quadratic formula does for you is actually tell you if you factorize, this is what you would get. So really, factorizing when we want to solve something equal to 0 is the method. So there's a 2t in common, so we pull this out. So we get t squared minus 6t plus 9 is equal to 0. And we can factorize this again because this is t minus 3 squared is equal to 0. So we know that the particle is at the origin when time is equal to 0 second and when time is equal to 3 seconds. Question B. We want to know when the particle is at rest. At rest means that the velocity is 0. So first we need the velocity. We know that the velocity is the derivative of position. So we have two expressions for position. We have the original one, which is a sum, and this factorized one. But if we use the factorized one, we'll have to use the product rule, and that doesn't seem like a very good idea. So we will go back and use the initial one. So we're going to get 6t squared minus 24t plus 18. And we want to solve v equal to 0. So v is equal to 0 if and only if 6t squared minus 24t plus 18 is 0. And we see that we can factorize out 6. So let's do this. 6 times t squared minus 4t plus 3 is equal to 0. As usual, we're going to be trying to factorize for about 20 seconds, and if after 20 seconds we still haven't been able to factorize, we'll move on to the quadratic equations. So we're trying to create a 4, so 3 under 1 should help, and we want a negative 4, so this is how we're going to get it. So we get 6 times t minus 3 times t minus 1. A product is 0 if and only if, so 6 is 0, that's not happening, or t minus 3 is 0, or t equal to 1. So we know that the particle will be at rest after 1 second and after 3 seconds. These are the answer to our first two questions. Question C. We want to know when the particle is traveling in the positive x direction. So this is your axis. So your particle would be moving this way, and if your particle is moving this way, x is increasing. If x is increasing, its derivative will be positive. So traveling in the positive x direction means that v will be positive. So we already know what the velocity is from the previous question. And from the previous question, we have two expressions for the velocity, one in expanded form and then the other one in a factorized form. So we can see that velocity is a polynomial of degree 2 in terms of t. So if we sketch the graph, we're going to be getting a parabola. And thanks to this second expression, we can get the t-intercepts, so that they're going to be 1 and 3. And with that, we can sketch velocity because we know it's a parabola opening up. So it will look like this. So that's the graph of y is equal to velocity in terms of t. So here it's t, and here I'm getting y. The reason why I stopped the graph at 0 is because in physics, time starts at 0. Now we have everything we need to answer the question. So we were wondering for which value of t the particle was traveling in the positive direction. And we said that that means that the velocity is positive. So it's this part of the graph, which in turn correspond to this part and that one. So we can see that the particle is traveling in the positive x direction when time is between 0 and 1 second, or time is greater than 3 seconds. Of course, traveling in the positive x direction is the same as traveling to the right. Next question, we want to know when the particle is traveling in the negative x direction, so to the left, for the same reason that corresponds to negative velocities. So we look at the graph again, and we can see that the velocity is negative when time is between 1 and 3 seconds. We now want to know when the particle is accelerating, and we are reminded that this means that the acceleration is positive. We know that the acceleration is the derivative of velocity. So what we will just do, we get the expression for velocity we already calculated and differentiate that. We get that the acceleration is going to be equal to 12t minus 24. Now, when is this positive? Either we can just solve the equation. The acceleration is positive if and only if 12t minus 24 is positive, which happens exactly when 12t is greater than 24. You get this by adding 24 to both sides. And now that means if you divide by 12, that t is greater than 2. Since you're dividing by something positive, you don't have to change the inequality. Of course, you could also do this graphically. If you wanted to represent the acceleration in terms of time, you can see that the acceleration is equal to 0 when time is 2 seconds. And that's a line going up. So we recognize the equation of a straight line. So that's y is equal to the acceleration in terms of t. And we can see on this graphic that the acceleration is going to be positive, will correspond to this part. So that's when t is greater than 2. Question F. So when is a negative? So the acceleration is negative. In other words, the particle is decelerating if, so same thing, just write down the formula you have for acceleration, try to see when this is negative, and we're going to get 12t is less than 24. Again, we divide by 12, and we get t is less than 2. Again, we could have done this by looking at the diagram. Your acceleration is negative when t is less than 2 seconds. And as usual, we make sure we add a sentence with our conclusion. Now we put everything together. So we're going to be sketching 3 graphs, and we're going to try to do it in such a way that the times line up nicely. By this, I just mean that this 1 second corresponding to position is right above the 1 second corresponding to velocity and right above the 1 second corresponding to acceleration. Let's sketch those graphs. Well, we've done it already, and I'm starting with acceleration because that's the easiest. The graph is just a straight line with t-intercept equal to 2. For velocity, we know that we're just getting a parabola with t-intercept equal to 1 and 3, whereas x of t is a cubic, and we said that the t-intercept was 0 and 3, which is visible in this expression. Now we notice that we have a square on the t minus 3 factor. That means that at 3, the curve stays on the same side of the t-axis. And in order to know which one, we just need to look at the limit as x approaches infinity. And we can see from this expression that this is going to be plus infinity. So we know that this goes to infinity here, then it stays on the same side. So from this, we know that there has to be a maximum somewhere here. And where exactly is a good question. Well, that's going to be a local maximum, so there's going to be a horizontal tangent. Horizontal tangent means the derivative is equal to 0. So if you just go back to the derivative of position, which is velocity, you see where your horizontal tangents are. There's one when t is equal to 1 and one when t is equal to 3. So this drawing is imprecise. The maximum should be right above t equal to 1. I think it's really nice to have all those curves one on top of each other because you can really check that everything makes sense. Initially the particle is at 0 and then x starts increasing. If x increases, that means its derivative is positive, which is what happens. Then you get this horizontal tangent, meaning the derivative is 0, which is what you can see here. Then its derivative is negative, which is why it's decreasing. Until you get to t equal to 3 where the derivative is 0 again, and that gives you this horizontal tangent. Then the derivative becomes positive, which is why x of t increases. And we can see the same type of consistency between the velocity and the acceleration. When t is between 0 and 2, acceleration is negative, and acceleration is the derivative of velocity, so velocity should be decreasing. It is. When you get to t equal to 2 seconds, acceleration is 0, which means there should be a horizontal tangent on the graph of velocity. Well, there is. Then acceleration becomes positive, which means velocity should increase. And we could also use the fact that the acceleration is the second derivative of position. Therefore, it gives the concavity. When acceleration is negative, your function should be concave down. It is. Then acceleration becomes positive and your function becomes concave up. At t equal to 2, we go from concave down to concave up. That corresponds to a point of inflection. And indeed, we have a point of inflection here, because imagine you're driving on this curve. You would have your wheel turn to the right on this part, and then suddenly at the point of inflection, you would need to start putting your wheel to the left. That's exactly what a point of inflection is. So far, we've been focusing on calculus. Now let's try to see how the particle moves along the line. When time is 0, the particle is at the origin. Then x increases for 1 second. That means my particle travels to the right for 1 second. And I need to calculate where it actually gets. Well, I can do this by calculating x of 1. Where is the particle after 1 second? And I can sub in the formula we have up there. We get 2 minus 12 plus 18. That's minus 10 plus 18, and that's 8 meters. So my particle gets there 8 meters away from the origin after 1 second. At that point, x starts decreasing, and it's going to decrease until x is 0 after 3 seconds. So it's going to be decreasing until the particle goes back to the origin after 3 seconds. So this is where we are. And now x increases again, this time forever. If x is increasing again, that means my particle will turn around and start moving this way. So here I didn't really draw everything exactly on the line, otherwise we wouldn't see anything. Let's see how this is consistent with the rest of the things we have. When v is positive, it means the particle is traveling to the right. That's what happens between 0 and 1 second. Then v becomes negative, that means the particle traveling to the left. That's what happens between 1 and 3 seconds. And after that, v is positive, meaning that the particle is traveling to the right again. In order to see what acceleration means, it's good to go back to physics. So, if you have a positive acceleration, it really means that a force is pulling you to the right. That's Newton's second law of motion. So what this says is between 0 and 2 seconds, there is a force pulling the particle to the left. So indeed, your particle starts going to the right, but something pulls it to the left, so it slows down and slows down until it stops. Now the force is still pulling it to the left until it gets there after 2 seconds. At that point, something starts pulling it to the right. So if something pulls it to the right, it slows down and slows down and slows down until it ends up going to the right. Let's now look at the speed. Remember, the speed is the absolute value of velocity. So in order to sketch the graph of the speed, we're going to start from the graph of velocity, which we already have. This green graph is the graph of velocity. Now we know that speed is the absolute value of velocity. So here, when x is between 0 and 1 second, we're taking the absolute value of a positive number, so it's the number itself. And it's the same thing when t is greater than 3. Now when t is between 1 and 3, taking the absolute value just changes the sign, which means we're reflecting the curve in the x-axis. So what is in red now is the graph of speed. Question H. When is the speed increasing? Well, we can do this just by looking at the graph. It's increasing here and there. That's our increasing speed. The speed is increasing when time is between 1 and 2 seconds, and also when time is more than 3 seconds. Question I. When is speed decreasing? We can see that it corresponds to these two parts of the graph, which means that speed is decreasing between 0 and 1 second, and then again between 2 and 3 seconds. Note that in everyday English, accelerating and increasing speed would be the same thing, and decelerating and decreasing speed would be the same. But not here, because accelerating just means the acceleration is positive. For instance, let's look at what happens to the particle between 0 and 2 seconds. So if you remember correctly, the velocity is 0 at this point, and your particle is moving to the left, so your velocity is negative. So your velocity will be, when the particle is here, your velocity will be 0, and then maybe -1 meter per second, and then -2. So your velocity is decreasing, so it shouldn't be a surprise that between 1 and 2 seconds, the particle is decelerating, if decelerating means that the acceleration is negative. Now, when the particle is here, its speed is 0, and then it starts moving to the left faster and faster. And if it moves faster and faster, indeed, its speed is increasing. So there's no contradiction with math. The problem is there's a conflict with the way we use the words in everyday language. Another way of looking at it is looking at acceleration as a force. Newton's law of motion, we'll come back to that, says that a positive acceleration means a force is pulling the particle to the right. And a negative acceleration, a force is pulling the particle to the left. So let's go back to what's happening between 1 and 2 seconds. Between 1 and 2 seconds, your acceleration is negative, so it means something is pulling the particle to the left. So if initially the particle was at rest with the velocity equal to 0, something pulls it to the left, it's moving to the left faster and faster. That seems very natural. So the speed will be increasing and the velocity, as we said, will be decreasing. This interpretation of acceleration as roughly the same thing as the force pulling on the object is a very powerful one. Maybe you remember that between 0 and 2 seconds, so all of this, acceleration is negative. And that corresponds to what happens. Initially your particle moves to the right, but a force pulls it to the left, so it slows down and slows down and slows down until it stops. The force keeps pulling it to the left, so now it's moving faster and faster to the left. And then, after 2 seconds, acceleration becomes positive, so now there's a force pulling it to the right. So your particle is slowing down and slowing down and slowing down until it stops, and then this force pulling it to the right will take it to the right forever. Thank you for watching this video on the motion of a particle in one dimension using calculus. If you want to take it one step further, look at the video on motion of a particle in 2 dimensions. So that means the particle is moving in a plane.